So imagine now that we have the Riemann sum for the function 1 minus x squared on the interval a, b. And we're going to split that in n equally spaced subintervals. So if n is equals 4 and I decide that ab is 1, 3, I can do the midpoint Riemann sum for that. Also, I'm going to try to do the left Riemann sum for AB being 0 and 3 and n equals 6. So now let's take a look at the midpoint Riemann sum. So notice that now we have that the function is not like we did before, that it was positive and above the x-axis, but now we're going to have a function that is that has a lot of parts below the x-axis. So because we're going between 1 and 3, notice that we're going to get that the rectangles, the height of the rectangles are going to be negative. We have the height of the rectangle here being a negative amount, here another negative amount, and so on. The basis is still going to be 0.5. We're moving here from 1 to 1.5 to 2.0 to 2.5 to 3.0. And so we're essentially going to do the same Riemann sum. When we calculate the area of all this and we add them up, turns out that the Riemann sum for this is going to be minus 6.625. So there's a key difference here to what we did before, and is that notice that the sum of these areas is going to be negative because we're considering one of the dimensions as negative. We're considering the length of the rectangle as negative. Now, if I consider the one from 0 to 3, notice that I get different things going on. I'm going to have a piece of 1 minus x squared that is going to have positive rectangles, and I'm going to have a big part of also 1 minus x squared that is going to be produced with negative rectangles. Okay? So what's going to happen is that the left Riemann sum from 0 to 1.5 is going to be accounted by everything in green. So notice this is a positive area, 0 area over here, because we don't have really a rectangle here. And then we start adding up negative parts. The area of the positive is going to be 0.875. The area of the negative, which goes from 1.5 up to 3, is going to be minus 475. So the resulting Riemann sum of everything is just going to be the addition of those two parts. And if I add 0.875 to minus 475, I'm going to get actually minus 3.875. So it's like they're subtracting. So positive areas are going to be subtracted with the negative areas when we have Riemann sums. So now the general idea of this is going to be the same if I go for a function that is below the x-axis. Notice that I can always make my partition, find my xi values. In this case, I'm going for a point maybe in the middle or in the left side. It depends on where I want to choose it. And in here, the sum from k equals 1 to n of f of x star delta x is going to approximate the negative of the area of the region bounded. Notice that we're not saying that by itself the area is negative, because the areas are always positive. But just because the area is below the axis, that we're going to multiply that area by a minus. Okay? Now, let's talk about positive and negative contribution. So if we have in general a function, and then that function has certain areas above the x-axis and certain areas below the x-axis, then we need to separate those Riemann sums. We need to separate those areas, and we are going to account them by each one of them by itself. In that way, we get to do everything that is above the x-axis. We can account that for a positive area, and anything that is below the x-axis, we can account for that as a negative area. Now, with that notion, we can talk about the concept of net area, which is essentially what you will think. If you have positive areas and negative areas, you're going to add all the positives and you're going to subtract all the negative areas. Okay, so the definition of that is: consider a region R that is bounded by the graph of a continuous function f, the axis x, and the numbers x equals a and x equals b. The net area of the region R is going to be the sum of the areas of the part with R lies above the x-axis minus the sum of the areas of the part that lie below the x-axis. Okay, so the general idea for that is exactly what we've been doing before. We can just go ahead and do Riemann sums for this. We first have a certain partition. Here we see an example with 6 subintervals of this partition, and then we just do an example, or we do a partition with 40 subintervals. So you can see that we have exactly the same situation. We approximate, and we're going to reduce the error the more that we make approximations. Okay, now if then f is a continuous function, then what's going to happen is that it's going to be very reasonable to expect that the Riemann sum approximation are going to approach the exact value of the net area. And as the subintervals go to infinity, the length of the subinterval go to 0, and this approximation pretty much gives me the area. So the limit of that sum of that Riemann sum is going to give me the area. Okay, now we can define then at this point the general Riemann sum, and we're going to define the general Riemann sum as given an interval a b with a partition of subinterval xu x1 x1 x2 up to xn minus 1 xn, then being delta xk, the length of the subinterval xk minus 1 to xk, and xk star any point in that interval, then I can, given that partition, and notice here the length of each of the intervals might be different, but their general Riemann sum is just going to be the sum of f of x star, given me the height of the rectangles, by delta of xk, which is going to give me the width of the rectangles. As you can see, we have different sizes here, and this is going to be called the general Riemann sum of f for AB. Now, the discussion from this is going to be that from what we saw, taking the limit when delta is going to 0 or when the subintervals are going to infinity is going to be a new object that we're going to call the definite integral. And definition follows as this. A function f is going to be defined in the interval ab, is going to be integrable on ab if the limit when delta going to 0 of f of x star delta xk exists and is unique over all the partitions of ab and all the choices of xk star on a partition. So it doesn't matter if we're doing left Riemann sum, right Riemann sum, middle Riemann sum, depending of the delta size of the subintervals, it doesn't matter. It's always going to go towards the same number in the limit, and that number is called the definite integral from a to v. So now you can see the relationship between area and antiderivative. Now let's see a little bit of the anatomy of the definite integral in the Riemann sum. We're going to have here the symbol of the integral, and this is going to tell us where are we integrating, what is the interval. So the lower limit of integration is going to be, well, the starting point of the interval, and the upper limit of integration is going to be the end point of the interval that we're going for. The function f of x is of course the function that we want to integrate or get the antiderivative. And delta x is just telling me what variable we're really integrating for. On the other hand, this is going to be equals to the limit when the width of the subintervals is going to 0 or the number of the subintervals is going to infinity, of the Riemann sum of k equals 1 to n of f of x star delta xk. Okay? Now, thanks to that, we're going to have some particular properties that we can apply. Notice that if I have the integral from a to b of f of x dx, this is just the same if I say the integral of a to b of f of w dw. We just need to take into account what is the independent variable that we're using. In this case, we're using x. In this case, we're using w. And in this case, we're using x. But all those mean the same thing, and it's going to be the same area. Now, once that we have this, then we can talk about integrable function. If f is a continuous function on the interval ab and is bounded on the interval ab, with and we can say that it has a finite number of discontinuities, then f is integrable. Okay, so it might be continuous or bounded or have finite number of discontinuities. That is going to make it integrable on that interval. Okay. So let's take a look at an example with areas that they have different values, positive and negative values. Sometimes, because of the reason of or the shape of the curves, we're going to be able to approximate the areas with regular geometry. So in this case, notice that we have like parallelograms going on in here with some triangles. So if we don't have the information about what the area is, which in this case we actually do, like for example this for this function f of x between a and b, this piece is area 1, this piece over here is area 2, and this piece over here is area 3. The overall integral, the net area, is just going to be the integral of a to b of f of x dx, and that's going to be represented by the area above the x-axis, which is in the area 1 and in the area 3, or region 1 and 3, minus the area below the x-axis, which is going to be here, the region 2. Okay? And given that, then we can start talking about approximating function via the Riemann sum, or we can say, well, the Riemann sum between these two points can be approximated by now the integral. And that's going to be very good because we already know how to do some of these antiderivatives. So it's going to mean that I don't have to do the Riemann sum for this. I don't have to think about an indefinite amount of subintervals, but instead I'm just going to do this with the antiderivative. So now the Riemann sum for the interval 1 to 3 of the function 3x squared plus 2x plus 1 is just going to be the integral from 1 to 3 of 3x squared plus 2x plus 1. Okay? Now, we'll go back to this and what this means once that we can talk about the fundamental calculus theorem, and that's going to show me how to solve an antiderivative with these numbers in the mix. For now, let's go back to the notion of finding the area with geometric figures. So for example, we can use familiar formulas of area to find the value of the following definite integral. We have the function y equals 2x plus 3 between 2 and 4. And so notice this is going to be height 7, this is going to be height 11, and we're going to be able to find out what the area is. So let me show you that really quick in the board. Okay, notice that this is a line, but if I move up to this point, so let me see how can I do this. Well, I have a line, okay, and it's between 2 points. So we have this situation, and the points are 2 and 4. So this is 2 and this is 4, and this side measures 7 and this measures 11. Notice that I can split this into I'll loosen this piece. You see, now I can make this a triangle in a rectangle, in a rectangle, yeah. So this measures both 7, okay, and the difference between 2 and 4 is going to be 2. So of course the area of this rectangle, I'm going to call it region 1. This region 1, the area of that is going to be 2 times 7, which is going to be 14. Now this second area, which is going to be the area of this triangle, is going to be base 2 by height. And notice that because this is 7 but everything is 11, this is telling me that this little piece is 4. Okay, so it's going to be 2 by 4 divided by 2, and so that area is going to be overall 4. So if I want to classify the full area, I'm going to do R1 plus R2, and I'm going to get 14 plus 4, and that's just 18. So I can say, well, the integral between 2 and 4 of the function that we have here, which is 2x plus 3, delta x is going to be 18. Which coincides with what I have here. Now, let's see another example. So in a similar way, if I go for the area given by 2x minus 6 between 1 and 6, turns out that I'm going to have two triangles. Okay, this triangle is 3 by 6 divided by 2, so it's going to be 18 divided by 2, which is 9. This area over here is going to be 4 by 2 divided by 2, which is going to give me area 4. But now, because this is a net integral here, the whole area of this is going to be 9 minus 4, which is going to be 5. Okay, so in this case, in this second example that I'm going to go for here, okay, if I account the integral of 2x minus 6 delta x between 1 and 6, that is going to be all the positive area minus the negative area, and so it's going to be positive. We had that it was 9 and the negative area 4, so this is a 5, and this is pretty much what we can get from this. Okay, one example more. We have now we can use familiar areas to get another type of function. So we cannot know the area of a circle. So for example, we have a function that is describing a semicircle like this one, y equals the square root of 1 minus x minus 3 squared, and that's going to be between 3 and 4. Then I can actually find what this is going to be. Notice that this is a radius 1 semicircle. And normally the area of a circle is pi r squared, but I'm just taking a quarter of that circle. So I'm just going to divide by 4, 1 over 4 pi by 1 squared. So this is going to be 1/4 over pi. And in a similar fashion, then I can say, okay, so this means that the integral between 2 and 4 of 1 minus x minus 3 squared delta x is just going to be 1/4 of pi. So as I'm showing, there's just a very quick relationship between the integrals and the area below the curve of the function. Another example here, we have the following figure that shows the graph of a function f with the areas of the region bounded by the graph in the x-axis. Notice that this is the function f of x. We're going to analyze what is the total area, and this is just, well, the area from A to B, or from B to C, or from A to C as well, and from B to D. So notice that we can find the values for all these integrals here. So from A to V is easy, just only from here to here is 12, and we're done. From C to V, notice that we're going in this direction backwards. So going in this direction backwards is also going to give me a negative. So it turns out that this is minus 10, but because it's going in the opposite direction, we're going to get that this integral is 10. Okay, we'll see that property more later, but take this into account. Normally we should go from B to C, and that will be a minus 10, but because we're going from C to B, then it becomes minus 10, so plus 10. Now the area from A to C, notice that is all the positive minus the negative, so it's 12 minus 10. We're going to have that this integral from A to C is going to be 2. Now from B to D is a similar situation. We have this negative area plus this positive area, and this is minus 10 plus 8. That's going to be minus 2. Now, then just with the example that I show, if we have the reverse of the limit of integration, or we have identical limits, we're going to have the following property. So if the integral of b to a of f of x dx is equals to minus the integral from a to v. So notice that we have a flip in the sign, if we have a flip in the order of integration. Now if we have the integration going from a point to itself, then that's going to be 0. Now let's talk about splitting areas. So if we have a point P that lies between A and B on the intervals, then the integral from A to B might be split into integrals. Notice that that's a natural consequence of area. If I have the area from A to B and I have a point in the middle, I can do the area from A to P and the area from P to B, and so I can represent the integral from A to B as the integral from A to P and then from P to B. Okay, so it's natural to split areas if I have points in the middle, and those points sometimes are going to be very convenient. In the same fashion, then thanks to that, I can find pieces of the area if I don't want to find anything. So for example, we can find the area of B as a subtraction of a larger area minus a small section. So here we're gonna go for the area of A to B, but we can do the area from A to P in general. So the area from A to B can be extracted from doing the area from A to P minus subtracting B to P, the area from B to P. And so this is all a play on moving and subtracting areas. Now, another thing that we can do is we can make interpretation about what is the integral of the absolute value. What is the absolute value going to do? Well, the absolute value of a number converts negative numbers in positive numbers. So with functions, it's going to do something similar. What's going to happen is if I have regions that are negative, the absolute value is going to flip them around and they're going to become positive. Notice this function here. We have two areas, and our area R1 is negative, and area R2 is positive. So when I do the absolute value of f of x, this area is reflected in the axis and it becomes positive, and then the positive area stays the same. So in general, the integral from the absolute value of f of x from A to V is going to be the area of R1 plus the area of R2. No change in the sign. Okay, be careful with this particular example. The absolute value of f of x fixes the problem with the sign and just give me the positive area. Now, some properties of the definite integrals. First, the ones that we saw in the definition, the integral from a to a of f of x is 0. The integral from a to v of f of x can be seen as minus the integral from a to b of f of x. And thanks to the derivative nature or the antiderivative nature of the integration, then we have that integration of f plus or minus g is going to be the integration to a to b from f plus or minus the integration from a to b of g. And if we have a constant, we can take it out of the integral in the same way that we could pull out constants out of the derivatives. And because we can accommodate areas, then the area from a to b is just the same that the area from a to p and plus p to b. That's having areas that have a point in the middle. The final property is the fact that if we have that the absolute value of f is integrable, then the integral of the absolute value of f of x is just the sum of the areas of the regions bounded by the graph of f in the x-axis in the interval ab. Now, if we have a non-negative integral, from that we can conclude that the integral of f of x is going to be positive if the function is positive. So for example here, notice that this function is always positive, so all the area is always positive. Now, from that, something that comes to light is if you have a function that is bigger than another one in the interval AB, then it makes sense that the interval of the biggest one, the area of the biggest one, is going to be larger than the area of the smallest one. So you can see that here in the graph, we have that the function f of x is in general bigger than g of x on the interval AB. The graph of f is always on top of the graph of g of x. And so that means that, notice, f is going to have a larger area under the curve than g. Another thing that happens is that if we have that the function is bounded, so for example, if f of x is bounded between constant small m and big M, then we can integrate on both sides and say, well, okay, well, if, and let me just show you this on the board. But essentially is, if you have that f of x is bounded, you can say, well, f of x is bigger than m, and it's smaller than big M. So you do integration on both sides. And so what's going to happen is, of course, using antiderivatives, this is going to be m minus b minus a. This is AB. Okay. This is what's going to end up happening. Notice that this is the length of the integral, so that's why it becomes like this. Okay. Finally, a couple more properties then we can summarize here from what we just saw. If f of x are integral function where b is bigger than a, so if the function is positive, the area is going to be positive, the net area or the integral is going to be positive. If f is bigger than g, then the integral of f is bigger than the integral of g. And if the function is bounded, then the integral is also, or the area is also going to be bounded by those constants plus the length of the area. Now, on part 2, we're going to go for some more examples to calculate in doing sketches, finding these particular examples. So tune up for the second part of section 5.2.